So we're in section 14.5. So we have for this, what we're talking about here is we have a surface, z equals f of xy. And we're going to say that it has, z has continuous first partials, and R is going to be a closed bounded region in the xy plane. So R is our region in the xy plane. We want to come up with a way of finding the area of the surface, area of this surface bounded by this region. So let's draw a picture here. It's always nice to be able to visualize what we're doing. So we have a surface. Here's our surface up here. So this is z equals f of xy. And we have we're talking about some region in the xy plane down here that's our boundary. So there's R. And what we're going to do is we're going to, just like we've done with everything else so far, we're going to divide this into little pieces. And we're going to call this the area of this little piece of surface, delta S sub ij. And we're going to say that we're interested in this point here. We're going to call this point ij. And we can project this down into the xy plane, and we get a little rectangle or a parallelogram in the xy plane. So when we project this down, we get a little delta y sub j and a delta x sub I. So a little piece of area in the xy plane. And piece of ij corresponds to x and some xy in the some coordinate xy in the plane. And then what we're going to do is we're going to take the sum of these little delta S sub ij's over the region to come up with our surface area. So to come up with this sum, what we're going to do is approximate this small little piece of surface by the portion of the tangent plane that lies directly above this little delta S sub ij. So that's the approach that we're going to take. So approximate delta S sub ij with the portion of the tangent plane directly above, and we're tangent at points of P sub ij. So what I'm going to do next, we'll draw a picture. We'll leave the surface off here, but we'll draw a picture of that portion of the tangent plane and come up with a way that we can find an expression for this delta S sub ij. So this is our approach. All right, so let's draw the portion of the tangent plane. So here are our axes. And here's our tangent plane. The little portion, I'm going to magnify it a little bit here. And here's P sub ij. And I'm going to extend the sides So here are the, I'm going to draw these in dotted lines for this other, for the other two sides. So there's our portion of the tangent plane. And I'm going to call the area of this piece delta t sub ij. What we're going to do is represent these two sides of this little piece of the tangent plane with vectors. So this is going to be vector A, and this is going to be vector B. And again, this corresponds to a little element of surface, delta x sub I and delta y sub j, in the xy plane. So if I project this down, you get a little portion again in the xy plane. We get a little rectangle in the xy plane. Fix my dots here. There we go. And this would be delta y sub j, and this side would be delta x sub I in the xy plane. So we're projecting that down, and we get a little rectangle. So these two vectors lie along the side of this little parallelogram that is a portion of the tangent plane that's directly above that delta s sub ij. So starting, what we're going to do is come up with expressions for these vectors, and then the area of this parallelogram is the magnitude of the cross product of those vectors. And then we can sum that magnitude of the cross product over the region, and we get the area, we get approximately the area of the surface. So starting at p sub ij, my vector A is going to be delta x sub I in the I direction plus the slope delta f sub x at that particular point times delta x sub I k hat. So the slope times the change in the x direction gives me how much that vector has changed in the z direction. And vector B is going to be delta y sub j hat plus the partial with respect to y at that particular point times delta y sub j in the k hat direction, in the z direction. So those are expressions for our two vectors that are the sides of these parallelograms. And the area of the parallelogram of delta t sub ij is the magnitude of A cross B. And then we're going to sum these areas over our region, and we get an approximation for the area of the surface. As we take that delta x sub I and delta y sub j, the limit as that gets smaller and smaller and smaller, then we end up with a representation of the area of that surface. So let's form this cross product, A cross B, and we'll see something really nice come out. Doesn't look like it will at first, but it comes out really nice. So we get I hat delta x sub I 0 in the j direction, and for k hat we get f sub x at x sub I, y sub j, delta x sub I. And for B we get a 0 we get a delta y sub j and an f sub y at our particular point. And when we form this cross product, we end up with, so we form the cross product and we're going to be able to factor out a delta x sub I, delta y sub j. So what we end up with is a minus f sub x, x sub y, y sub j, I hat, minus f sub y at our particular point, x sub I, y sub j, j hat, plus k hat, and we have a common factor of delta x sub I, delta y sub j. When we form this cross product. Well, I can call delta x sub I, delta y sub j, delta a sub I. That's the small change in area in the xy plane. We take the magnitude of this cross product, so the magnitude of a cross b. When we take the magnitude of this, we end up with the square root of the partial with respect to x at our point squared, and I hopefully this expression looks somewhat familiar, plus the partial with respect to y at our point, and we're going to square that, plus 1 delta a ij. And the total surface area over the region is going to be the sum of all of these little pieces of area that we get from the portions of the tangent plane. Well, here we have a function of x and y times delta a sub I. We're taking the limit as delta a sub ij gets smaller and smaller and smaller. We're summing that over the region. Well, this will correspond to our definition of a double integral, as we take the limit as that delta a sub ij gets smaller and smaller. So our surface area over the region is going to be the double integral over our region of f sub x, partial with respect to x, squared, plus f sub y squared, plus 1, and we're taking the square root of that. dA. Does this expression look like something we've used before? We take a derivative and square it, add 1, take the square root, and we're taking the sum of that. This looks like our arc length integral. For our arc length integral, we just had one derivative in there. We write f prime squared plus 1, take the square root, and we're summing that to get the arc length. So this looks like an arc length integral. Very similar idea to how we came up with arc length. You'll often see this written as our surface area equals a double integral over R of ds. And this quantity, square root of f sub x squared, f sub y squared plus 1 dA, we call that the surface area element, or surface area increment. Just like we talked about the arc length element or arc length increment, this is our surface area element or surface area increment. So this quantity f sub x squared, f sub y squared plus 1 square root times dA comes up in a lot of contexts, so we call it ds. So looking at, so this gives us a way of finding the surface area of a surface given by f z equals f of xy over a region R in the xy plane. Now looking at this expression, what are you going to guess about surface area integrals? They can often be very difficult because you have this f of x squared, f of y squared plus 1. You're taking the square root of that and integrating. So they often, surface area integrals are difficult. So the ones that we end up doing, the surface tends to be pretty nice surfaces, so that when we do these things, we can actually come up with something that we know how to integrate. So questions on our development here. But this idea that we used, where we took the tangent plane and took the cross product of the two vectors to get the area of that little piece of the tangent plane, it's such a nice idea to use that and sum that to get a surface area of a surface. And what was it? Didn't you tell me last semester, Max, that Mr. Lowe always says a cross product is an area? Didn't you talk about him saying cross products are areas? I thought you talked about that once. Maybe Mr. Lowe was talking about that. I don't know. But the idea of a cross product, using the cross product as an area, and that's a pretty common thing that we'll do. That we do when we're working with three-dimensional surfaces, is use that cross product to represent the area of something. So that's just a nice idea that we can use a cross product that way. So the dot product is a very friendly product. It's a nice product, but the cross product is probably a more useful product. All right, so let's look at some examples. Some examples where we can evaluate these integrals, set these up and evaluate them nicely. All right. So we want to find the surface area. Of f of xy equals 10 plus 2x minus 3y, and our region is the portion of the xy plane such that x squared plus y squared is less than or equal to 9. And that's what, just so you know, the colon, when we use it this way, we say that means such that. So what we're saying here is the region R is the set of xy such that x squared plus y squared is less than or equal to 9. So what's our region here? A circle. So we see a region circle, what should we be thinking right away? Polar coordinates. Very nice. All right. So this is not a bad. And what's our surface? What is this? It's a plane. So we want the surface area of a plane bounded by a circle. So we have this plane cutting. So if we think of the circle, extending the circle upwards, we have kind of end up with kind of an elliptical shape in space. All right. So f sub x. Nice, easy first partial. F sub x equals 2. F sub y equals negative 3. So our surface area is going to be the double integral over our region of the square root of 4 plus 9 plus 1. Square root of 14 dA. And we decided we wanted to use polar coordinates. So let's sketch our region here really quickly. I'm going to sketch a quarter of the region. Not 14, 1/4. 1/4 of our region, and our radius is 3. So what I'm going to do is, our surface area is going to be the square root of 14, since that's just a constant. The integral from Theta is going to go from 0 to 2 pi to get the entire circle. The integral from 0 to 3 of r dr d theta. Well, before we do this integral, what is the double integral over our region of dA? What does that represent? What's a double integral? When we're not putting anything in there, what's a double integral over our region of dA? That's the area of the region. This equals the square root of 14 times area of region. So here's one where we use geometry. What's the area of the region? The region's a circle. Radius 3. What's the area of that region? Pi times the radius squared. Square root of 14 times 9 pi. We could evaluate the integral and get the same thing, but the double integral over our region of dA is just the area of the region. Our region is a circle. We know how to find the area of the circle without doing the integration. So this surface area would be square root of 14, 9 square root of 14 pi. And we didn't even have to integrate. So this surface area integral turned out to be really easy. Let's see, let me look at So questions there? Let's look at another example. So here f of xy, we're looking for our surface area again. F of xy equals 2 plus 2/3 y to the 3/2. And our region is the set. We're looking for xy such that 0 less than or equal to x less than or equal to 2, and 0 less than or equal to y less than or equal to 2 minus x. So let's, first off, let's sketch our region. So 0 less than or equal to x less than or equal to 2. So x is going between 0 and 2. Y equals 2 minus x. That gives me a line. The y-intercept is 2. The slope is -1. So there's my line. And this is my region. So we take our partial f sub x. This turns out nice. F sub x is 0. Our partial with respect to y turns out to be just the square root of y. So our surface area integral, S, would be the integral x equals, x varies from 0 to 2, setting my rectangles vertical. Y equals 0 to 2 minus x of the square root of y plus 1 dy dx. And that was not a tough one to evaluate. Questions there? All right, let's look at a little more complicated example. For this one, we want the area of the portion of the cone z equals 2 square root x squared plus y squared. Inside the cylinder, x squared plus y squared equals 4. So let's make a quick sketch of what we're talking about here, just to visualize our surfaces. So here's our cone. Our cone looks something like this. And our cylinder, just going to sketch here. Our cylinder is coming up and cutting into the cone, like so. So there's our cylinder. And it cuts off a portion of the cone here. So we want the area of the surface area of the cone that's inside the cylinder. So this little portion of the cone down here. So we're looking at this part of the cone. So we need to find our region. We need to find our region in the xy plane. What part of this problem tells us our region in the xy plane? Well, look at the way I've drawn my picture there, and that gives us a hint of what our region in the xy plane is. What's our region going to be? Where does the cylinder intersect the xy plane? A circle, right? This x squared plus y squared equals 4 is our region in the xy plane. Our surface is above that circle in the xy plane. That's the portion of the surface that we're interested in. So our region in the xy plane is x squared plus y squared less than or equal to 4. So it's inside that circle. Now we need our partial derivatives. So the partial with respect to x, I get 2x times the square root of x squared plus y squared, x squared plus y squared to the negative 1 half. When I take the partial of this with respect to x, and it's a symmetrical equation, so I get x squared plus y squared to the negative 1 half, 2y. And this is starting to look like it might be complicated. Well, let's keep going. And before we do this, I'm just going to draw down here quickly a sketch of the region in the xy plane. And this is 1/4 of our region. So what does our region suggest again? Polar coordinates, since our region is a circle. All right, so let's find our radical that we need to put into our double integral. So we're going to have the square root of 4x squared over x squared plus y squared plus 4y squared over x squared plus y squared when we square each of these, plus 1. Now we need a common denominator. Let's simplify this before we put it into our integral. We need a common denominator to add all of these together. So my common denominator is x squared plus y squared. So I'm going to multiply this 1 by x squared plus y squared over x squared plus y squared. And when I do that, this equals (5x squared plus 5y squared over x squared plus y squared, which equals square root of 5. So it looked like it was going to be ugly, but it turns out nice. So our double integral, if we set it up in polar coordinates, so S would be the integral from 0 to 2 pi. The integral from 0 to our radius goes to 2 of the square root of 5 RD theta. Well, what's the integral, the double integral of RD theta? That's the area of that circle. So this turns out to be the square root of 5 times the area of this circle times 16 pi. Let's see, no, or 4 pi, sorry. Radius is 2. So this looked like it was going to be very difficult, looks ugly, turns out very nice. And we didn't even have to evaluate an integral. Questions there? All right, last thing I have is a couple of questions for you guys. So for these questions, z equals f of xy, and is greater than or equal to 0 over r in the xy plane. First question, is it possible for the surface area to equal area of R? If we have this surface and f of xy is greater than or equal to 0 over the region, is it possible for the surface area of the surface to equal the area of the region? I hear a couple of yeses. How would it work? Yeah, Carly says it's a plane. It's a plane parallel to the xy parallel to our region in the xy plane. So a plane parallel to xy plane. So that's a yes. 2. Second question. Can S be greater than the area of R? Max says yes. How is that possible? Right, exactly. This is pretty much always the case, that the area of our surface is going to be larger than the area of the region. Almost always. Because our surface is going to be more complicated than our area in the plane. And the last one. Is it possible for S to be less than the area of the region? Can our surface area be less than the area of our region in the xy plane? Brian says no. No? So Max says, can we have the function not actually over the region? So we're saying our condition is that that we're talking about this surface area of z over r in the xy plane. So our surface area can't be smaller than the area of the region. We can't have a surface and have the area shrink when we stretch it, basically. So this would be no. We can't have that area less than the area of the region. All right. I like these kind of thought questions. Homework. They're almost as fun as doing integrals. All right, there we go.